All right, so today, continuing on with this whole section of sets and probability and logic, which actually is a part of this as well. We're talking about probability. You're going to refresh your memory on how to find the different probabilities, the different types of formats that problems that deal with probabilities can be given to you as, and everyone should have a sheet with the notes on it. Yes? Yes. Okay, cool.
I didn't get one out.
Oh,
I have an extra one.
You have an extra? Okay. All right. So to start, probability, hopefully you guys remember, is the number of outcomes in the particular set or situation you're looking for divided by the total number of outcomes. So if you flip a die, if you roll a die, and you're trying to determine what's the probability of landing on a 4, your number of outcomes of that happening is what? 1 out of your total number of outcomes, because there's 6 sides to a die. Or if you're flipping a coin, which is the easiest one, what's the probability of you getting ahead? 1 over 2. Okay? Everybody have one? All right. Expected value. We talked about this at some point in time with probability. I can't remember exactly when, but basically, it is the expected number that you should get when you are performing something. So, prime example, if you play soccer and you're doing penalty kicks, and your probability of making the penalty kick is 1/4, and you kick 100 penalty kicks, how many goals are you expected to make? 25, because you take the probability of you making the goal, which is 1/4, and you multiply it by the number of tries that you have, which is 100. So you are expected, based off of your probability, to make 25 of those 100 penalty kicks. Yes?
Can we have Vanessa to check out, please?
Sure thing.
Thank you.
Complementary events. Complementary events. We talked about this before. That's everything that's not in a particular set. You can always find the probability of that happening by doing 1 minus the probability of the event happening, and vice versa. Any questions on that? Has anybody forgotten that?
A little bit. You just remind me.
Okay, as long as I remind you, that is what's important. These are the different types of ways that your information can be portrayed to you. You can have a combination table, okay? So, prime example, they tell you that you're flipping a coin and you're rolling a die, okay? And that is an example of a sample space that represents the different outcomes that you can have. You can have a head in every single one of the die possibilities, or you can have a tails in every single one of the die possibilities. You can also have this. It's a grid to represent that, not so much numerically, but more visually, okay? Tree diagrams. We did a lot of work with tree diagrams last year, okay? So, prime example, say getting 2 6s when 2 dice are rolled, okay? So, the very first dot here, this one right here, this is like you rolling the very first die, here and here. And this is you rolling the second die. You guys remember doing tree diagrams? Okay? And let's see. Who remembers? The probabilities that go along with the branches.
Oh, no, it's by fraction.
You can write as a fraction or decimal, but it should add up to be 1 whole or 100%, depending on what exactly you're given. Okay? Of course, just a simple frequency table. Say the days of the week that there are and the numbers of late students that show up or don't show up at all, because I'm still missing kids today for whatever reason. Two-way frequency table. We dealt with this when we were deep into statistics. Frequency tables grouped with the standard. Okay, don't forget about those. And then, of course, your classic Venn diagrams, which we spent Friday talking about. Okay? Any of these look foreign? We've dealt with them at some point in time. All right. The very first thing, or combined events, that is the union. That formula there that you see, the probability of A plus the probability of B minus the probability of their intersection. That is a very classic standard formula that's in your reference book. Okay? It can be used to find any one of those pieces of if you were looking for the union, but you had all those other pieces, you just plug in. If you didn't know the intersection, but you had all the other pieces, you can use that formula and plug in. Okay? Don't forget about independent events or mutually exclusive events. What does it mean to be independent? Add a little more.
Other events don't affect its outcome.
The events don't affect their outcome. Okay? So rolling a die and flipping a coin, those are clearly two independent events because, yeah, flipping a coin has nothing to do with rolling a die. Mutually exclusive. No.
Where only one outcome can work. So like you can't have a heads and tails.
Exactly. Did everybody hear what he said? Okay.
Oh, I remember that because
Then it was about laying on the side or something like that. Yeah, something like that. Same another concept where, like Lee said, like you can't have a heads and a tails when you flip a coin. Same thing when you draw a card, you can't have an ace and a king. Okay, like you're gonna pick a king or you're gonna pick an ace. You ain't gonna pick an ace king. Okay? No such thing. It's gonna be one or the other. Those are mutually exclusive events, and those are the formulas that are used to determine if events are independent or if they're mutually exclusive. Okay, that's how you show. That's how you show something is independent or mutually exclusive. Everybody got me? All right. Tree diagrams. Kind of already talked about them already. Don't forget with tree diagrams, you can also were used whenever we had replacement and without replacement. For example, let's say you have a bag that has some balls in it. You pick one at random. And then you pick another, okay? Do realize that these are the types of problems where you could deal with replacement or you could not deal with replacement. Does everybody understand what I mean by replacement and not replacement? And by putting it back. So prime example, let's take a look at this. Let's say you have some balls and they're being numbered. Clearly, you're given that the probability of it being even is 0.4. That means the probability of it being odd is 0.6, okay? Let's draw a tree diagram where you have replacement. So you're going to put the ball back in and you're going to draw again. I want everyone to draw a tree diagram to represent you picking a ball, putting it back, and then picking it again. I want everyone to draw a tree diagram on their paper to represent this. You picking a ball, putting it back, and picking again. Okay? Based off of this piece of information. The replacement one is pretty straightforward. Or it should be pretty straightforward. Okay? What are your two outcomes? Odd and even. What are their probabilities? Even is 0.4. And odd will be 0.6. Remember, your branches need to add up to be 1 or 100. Okay? So that's your first pick. But then you put the ball back and you pick again. What are your outcomes again? The same thing. So they're still odd and even, correct? And then your probabilities are still the same, correct?
Yes.
All right. Now below that, I want you to do another tree diagram to represent you not replacing the ball. In the notes. We're about to do desk in just a second. So you're finishing out that tree diagram to represent without replacement. Never mind, you gotta have the number of balls. Sorry, I was trying to do more because I'm like, I don't have an example of this where we can do it together. They're in your actual whiteboard stuff. So sorry, you can't actually do that. But let's say, let's say there were 10 balls. Let's say there were 10 balls, okay? So we're gonna add that in there. Now you can do it. So let's say there were 10 balls. Now do it. All right. So we picked the first time. What's the probability of it being odd? 0.6. And even? 0.4. Okay? So you pick that ball out and you don't put it back in. So now what's the probability of it being odd? This first branch right up here. It's going to be 5/9 or whatever that decimal is. Because once you picked it, you don't put it back, correct? And if it was originally 0.6, that's 60%. So that means that 60% of the balls, aka 6 balls, had to be odd to start with. Yes. As long as you round to 3 significant figures. Okay? What would be it for even? 4/9. Again, the branches have to add up. And again, you could do decimal. Just make sure you do 3 significant figures. What about odd if the first one you pick was even? It'll still be 6/9. And what about even? 3/9. Does everybody see how that goes? How it works? Any questions? Yes, no, maybe?
No.
Okay. Last bit, conditional probability. This is when you have the words such as given, such that, etc. Okay? If you went to go see the leopards, what's the probability that you also saw rhinos? Okay? Those are some other types of situations that you can deal with conditional probability. But the main thing is whatever is here, whatever is second, that is the condition. Okay? That is the condition. Any questions? So you would need the intersection between the two events, and then you divide it by the probability of that particular condition happening. So we're going to look at the second half of your pod. Okay? So go ahead and pull out your pod notebook. You put it away. This clearly was, no, you didn't do well. That could have been just all it was. No, it was a paper 2 question. So I'm handing out the remaining parts of your pod from today. You guys are going to add this to your pod, and you're basically going to finish it up, and then we'll check it. They deal with the probability. Bless you. Bless you. So go ahead and glue it in. Same date. All right, so we're trying to calculate the probability that the tourist chosen at random from a group saw a leopard, okay? So when you're trying to figure this out, well, saw a leopard. Is there any distinction of any kind? They didn't say only leopards or only leopards and rhinoceros or something like that? No. So you're looking literally at this entire L circle, which is how many? 12. Out of how many? 24. So your fraction, your probability is 12 out of 25. Yes, you could put the decimal, but make sure you round to 3 significant figures so you put the decimal. Now what if they only saw only one type of these 3 animals? Then what? Huh? How'd you get 16? 4, 9, and 3. So basically we're looking at this piece, and the bottom piece because it says only. So you were only looking at those there. So you add them all up, and you said it was 16? 16 out of 25. Very good. Now part 3. Saw only leopards given that he saw only one of the 3 types of animals. Keyword, given, which means what? Conditional probability. That right there is our denominator, the part that follows the given. So let's look at just the denominator. What is the probability that they only saw one of the 3 types of animals? 16 out of 25. Our answer to part 2, correct? And that's how a lot of times these problems do go, guys. If they give you a conditional probability, more than likely you already figured out the answer to the denominator or some part of the problem at a previous part, okay? So, out of those, what is the probability they only saw a leopard? Well, I'm talking about just in general. How many saw only leopards? 4 out of 25. So that will be your numerator. Keep, change, flip, because you can't leave it like that. That's a fraction within a fraction. And your answer will be, I heard it, 4 over 16. You could reduce it down to 1/4. Either one would be acceptable. But that's using the formula to get your answer. Questions? And the last one, D. If a tourist chosen at random from the group saw leopards, find the probability that they also saw cheetahs. How would you do that?
Okay.
Yes.
You would add 4, 1, 5, and 2 because all the people that's all of leopard.
Okay.
So that would get you a denominator of 12, but they want to know who that also saw cheetah, which would be 1 and 5, because that's the only thing that saw cheetah. That's all leopard and cheetah.
So my answer would be what?
6 over 12.
And that is correct. Or 1/2. Okay? This right here, this was indirectly conditional probability because it says if a tourist chosen at random from the group saw leopards, that was your condition. You were only looking at the leopard group. So technically that would be 12 out of the 25. Out of those, what's the probability they also saw cheetah, which would be 6 out of 25. Keep, change, flip, and that's how you get 6 out of 12. Questions on this pot at all? And that's pretty much the bulk of the probability, okay? Y'all didn't get too deep down into probability. It's pretty much just kind of just skimmed the surface with conditional probability, tree diagrams, sets, and everything like that. So we're going to do now some whiteboard practice, all right? Just make sure we're good.